Hello and welcome to this video for CE 108 Mechanics of Deformable Solids. So we are still in chapter 4. We're talking about the case of deformation that are due to axial loading. And so what we saw in the previous two videos is how to calculate the internal load and the internal normal stress, and how we can use this to calculate the elongation of the beam. So in this case, when you are facing typical problem of this, like the general methodology to follow will be the same as usual. First, you will need to draw the free body diagram, calculate direction of the support, and then based on this, apply the method of section to get the internal load. So the internal load in this case will be the first thing that you would need to calculate. And then once you have the internal load, you can calculate the stress within the beam. And if you have the internal load and the stress, then you can calculate its elongation. So this is what you will do for most of the traditional axial load problem. Then, that being said, there are some special types of problem which are called statically indeterminate, where you cannot directly calculate the internal load, because in this case, for those problems that are statically indeterminate, we cannot calculate first the reaction of the supports, which is the prerequisite in order to be able to calculate the method of section and to calculate the internal load by using the method of section. So in this case, for those problems which are statically indeterminate, for which you cannot calculate the reaction of the support, we will need to derive a new alternative method that is going to be specifically applicable to those statically indeterminate problems. So statically determinate problems can be faced in any case of the deformation, whether it's axial load, bending, shear, or torsion. But here we are going to see a first example of those statically indeterminate problems, and how do we solve them by considering first the case of an axial load deformation. So to illustrate this type of statically indeterminate problem, let's take an example. So for this, let's consider a beam that is attached to a fixed support at x equals 0, and that is also attached to a fixed support on the other extremity. So in this case, so this beam is going to have a size 2L, so it goes between 0 and 2L. We're going to say that this beam is attached to the point A to a fixed support, and also to a point C on the other hand. And in the middle of the beam, at the position L, which is going to be the point B, you have an external load. So you have a load P0 that is applied. And in this case, we are going to consider that both the Young's modulus and the area of the cross-section are constant. So they do not depend on x. They are homogeneous. They are constant as a function of x. They do not vary over the length of the beam. So in this case, the goal in this case will be to calculate the internal load as a function of x, and the normal stress as a function of x. And if we can get the normal stress x as a function, the normal stress sigma as a function of x, then we can estimate at which point x do we have the maximum risk of fracture, at which point x is the normal stress maximum. Okay, so let's assume that that initially we would apply the usual method for this. So we would start with the free body diagram, then we would identify the unknowns. So in this case, since it's since this is an axial load problem, and since there is no vertical force that is applied and no moment that is applied, I'm going to only focus on the normal component of the reaction of the supports. Here, those are fixed supports, so strictly speaking, there should be three unknowns, which are a normal force, a vertical force, a shear force, and the moment. But here, because there is no external moment and no external shear force, I'm going to disregard the shear component and the moment component of direction of the support, and only focus on the force that are along the x-axis. So in this case, so we have two unknown. Since you have an external load P naught that is pointing towards the right, it would make sense that the reaction of the support would point towards the left. So in this case, we can define the reaction, the normal reaction of the support at the point A, NA, and the normal reaction of the beam at the point C. So we can write this NC. So those are the two reactions of the support, again, because I'm disregarding here the moment and the shear force, since they are going to be equal to 0 in this case. Okay, so that was stage 2, identifying the unknowns. Now stage 3, equation of equilibrium. So we isolate the entire beam and rewrite the condition of equilibrium to find the value of the unknown. So we would write in this case that the sum of the forces along the x-axis is equal to 0, sum of the projection of the forces along x equals 0. So in this case, what do we have? We have NA, it has a negative projection, so it's minus NA. We have NC, also a negative projection. And then we have P naught, which has a positive projection. Sum of those forces is equal to 0. So in this case, we find that NA plus NC equal P naught. So that gives us one equation. Now we can write that the sum of the forces along y equals 0, but again, in this case, there's no forces along y, so we cannot learn anything from this. We can also write the sum of the moment is equal to 0, and again, in this case, we should choose the point through which we have most of the forces that have a line of action going through this point. In this case, we can take any point, like for example, the point A. We can write that the sum of the moment about A equals 0, but again, we would not learn anything about this because all the forces NA, NC, and P naught, they all have a line of action that is going through the point A. So they would have a 0 moment. So in this case, this equation would only tell us that 0 equals 0. So here in this case, we are in the case where we have two unknown, the two unknown being NA and NC, but we have only one equation, which is this equation number 1 here. So we have one equation but two unknowns. So mathematically speaking, we cannot solve it. We cannot solve this problem. This problem cannot be solved directly. To solve this this problem, necessarily, if we have two unknowns, we need to find two equations. So we need another equation. We need an additional equation that we can use to solve this problem. Two unknowns, we mean that we need two equations. We already have one, but we need another one. So in this case, this is an example of a statically indeterminate problem. A statically indeterminate problem is when you have more unknown than equation. So in this case, you cannot solve it directly. You need another equation, and in this case, this class of problem are statically indeterminate problems. So in this case, so we need an extra equation. So this equation that we need is going to come from, in this case, the geometry. Whenever you are facing a statically indeterminate problem, and when you find that you have more unknowns than equations that are given by the equation of equilibrium, then it means that you need an additional equation, and this equation is always going to come from the geometry. So in this case, the method that we will need to use here is we need to find what is this equation that is given by the geometry. So this is going to be called the equation of compatibility. So we need to get an equation of compatibility. The equation of compatibility will be an equation that captures some aspects, certain features of the geometry of this beam. So this is going to be something that captures the geometry of the beam. So there has to be a geometrical constraint about the geometry of the beam. And we can put this geometrical constraint into an equation. And this equation is going to give us the compatibility equation that we need to solve the unknowns. So again, in this case, whenever you face the statically indeterminate problems, you need to look at what's special about the geometry of this problem. What is the geometrical constraint that this beam has to fulfill? And based on this, we can get an additional equation. So in this case, if we look at this problem, like why is it statistically indeterminate? It's statistically indeterminate because there is a geometrical constraint that has to be fulfilled. And in this case, so this compatibility equation, in this case, this geometrical constraint is that because the beam is attached to a fixed support both at the point A and at the point C, then necessarily the length of the beam between A and C cannot change. So in this case, necessarily because the beam is attached at both its extremities, then the beam cannot be elongated. It's attached at two of its extremities, so necessarily it cannot change. The distance between those 2 points cannot change. So the elongation of the beam between A and C cannot change. So the elongation between A and C, the total elongation of the beam, cannot change. So this is in this case due to the fact that the beam has a fixed length because it's attached at both its extremities. So in this case, this equation of compatibility is only for this problem. The equation of compatibility will depend on each problem. Each new problem will have a different equation of compatibility because there will be a different geometrical condition that needs to be fulfilled. In this case, this is maybe one of the most simple cases where the case of the beam is attached at both its extremities, then the length is fixed, then it means that the total elongation is fixed. But this is not a general result. This is a result that is only valid to this problem. For every new statically indeterminate problem that you would be facing, you will need to figure out what is the equation of compatibility that characterize this problem. And it's going to be something that is problem specific. Different problems will have different type of compatibility equation. So now that we are aware of the fact that you will be facing both statically determinate problems, those are the problems for which you can fully calculate the supports, the unknown reaction from the support simply by expressing the condition of equilibrium. Those are the statically determinate problems. And you will also have statically indeterminate problems for which you will need an extra equation of compatibility. So then it means that when you will be solving these types of problems, then you will have potentially two types of methods depending on the characteristics of the problem. The beginning will always be the same. Step one will be about drawing the free body diagram and identifying the external forces on this free body diagram. So this doesn't change. Step two, identifying all the unknowns that are created by the reaction from the supports. This also doesn't change. Step three also doesn't change. You express the equilibrium equation on the entire beam. So this is also not going to change. Now, at this point, there is different possibilities. You need to consider different cases. At this point, once you have written the condition of equilibrium, you need to look like, do you have enough equation to solve the unknowns? Do you have enough equations, different equations, to solve the unknowns? Do you have more unknowns than degrees of freedom? Do you have more unknowns than equation? In this case, it means that you cannot solve them. You need as many equation as unknowns to be able to solve this system. So if you have enough equation, then you are in a case of a statically determinate problem. So those are the problems that we have been facing so far. This is the problem that you can directly solve using simply the equilibrium condition. And if you don't, if you have more unknown than equation, then you are in the case of statically indeterminate problems. So in this case, those are the problems that cannot be directly solved because you have more unknowns than degrees of freedom. And in this case, you have more unknowns than equations. And in this case, it means that you will need one extra equation that comes from the compatibility equation. So now let's look at those two cases. So let's focus first on the case where, yes, you have enough equation, you can solve the problem. This is the case that we have seen so far. So in this case, the method will be as usual. You will go with step 4. You will apply the method of section at each point x within the beam. Then step 5, you apply the condition of equilibrium on either the left or the right, so on the isolated region. And so based on this, you will be able to calculate the internal load. So this is going to give you the internal load, P of x. So once you have this, step 6, you will be able to calculate the stress. So in this case, the stress is sigma, is the load divided by the area of the cross section. And based on this, so you will be able to also calculate the deformation. So by using the deformation, the elongation formula, so by using the fact that the elongation between 2 points of the beam is the integral of the load divided by area of the cross section, Young's modulus, integrated over x between the 2 points. So in this case, since you have calculated the internal load, then you will be able to calculate the deformation. So now, this approach is not going to work if you have a statically indeterminate problem, because you cannot, you simply cannot calculate, you cannot apply the method of section directly because you have not found the unknowns. So in this case, so the step 4 that you will need to do in the case of statically indeterminate problems is that first you will need to find the equation of compatibility. So you will need to look at what is the geometrical constraints that has to be fulfilled in this problem. So is it that the elongation of the beam is equal to 0? Is it that some part of the beam have to have the same elongation as each other? Or so this is going to be specific to each problem, and we will see different examples of different equation of compatibility. Then once you have found this equation of compatibility, then the next step is that, so this is going to give you a geometrical condition, and you will need to express this geometrical condition in terms of the unknowns, because again, what we want to find is a new equation that relates the unknowns. This is the equation that we are missing. So we will need to translate this geometrical equation and to rephrase it into an equation that relates the unknown. And for this, we will need to use the method of section. So we will see an example later, but so we will need to use as a step 5 the method of section. Step 6 will be again to write the condition of equilibrium for the isolated region. So that's going to be step 6. Step 7. So now we will need to calculate the deformation in terms of the load. So this part, the step 5, 6, 7 are going to be the same as the step 4, 5, and 7 that you have in the case of statically determinate problems, but except that in this case we will calculate the deformation in step 7, but at this point the deformation will not be the final result. It's going to be a deformation that depends on the value of the unknown. So that's going to be an intermediate equation. This is the equation that is going to give us this new equation that we need that relates the unknown. Again, we are going to see an example next on how does it translate in practice. And then, so once you have done this step 7. So you will have now a new one new equation that relates the unknown. And once you have this new equation that relates the unknown, then it means that now you will be able to solve the unknowns. You will be able to calculate the value of the unknowns. And once you have the unknowns, then you can come back to the last step, which would be step 8 here, and would be the same as step 6, which is now that you can calculate the stress. Once you have the unknown, then you can calculate everything. You can calculate the internal load, you can calculate the stress, etc. So in this case, those are two different approaches. If it's a statically determinate problem, then you follow the usual approach. Method of section gives you the internal load, and based on the internal load, you can calculate the deformation. If you don't have enough equation, then you need to follow a reverse approach, where you calculate the deformation first in terms of the unknown, and you use this to get a new equation that is then ultimately allow you to calculate the internal load and the internal stress. So in the case of statically determinate problem, you first calculate the internal load and then based on this calculate the deformation. Now it is going to be reverse. In the case of statically indeterminate problem, you need to first calculate the deformation, and this is what is going to allow you to calculate the internal load and the internal stress. So this is a reversed approach. So let's come back to the initial problem now to see how we can apply those different steps. So again, we started with step 1. So free body diagram. Step 2, we identify the unknowns. So in this case, the two unknowns are NC and NA. Then step 3, we write the condition of equilibrium that gives us only one equation, which is that Na plus Nc equal P naught. That's the only equation that we get out of the condition of equilibrium. In this case, so we do not have enough equation to solve this problem. That's a statically indeterminate problem. And in this case, it means that we need another equation, which is the equation of compatibility. So that's, in this case, step 4 is the equation of compatibility. So in this case, the geometrical condition that has to be fulfilled is that because the beam is attached at both of its extremities, at point A and point B, then its length cannot change, which means that the elongation between A and C, sorry, this is the elongation between A and C, not the elongation between A and B. So the elongation between A and C has to be equal to 0. So then this is the equation of compatibility. That is step 4. So now we need to go back to the method that we described in the previous slide. So now we need to use the method of section. We need to use the method of section to calculate the internal load in terms of the unknowns. We need now to transform this compatibility equation, which is now a geometrical condition. We need to transform it into a new equation that relates the unknown so that we can solve this problem. So now we are going to be step 5, method of section. So let's use this. So in this case, we have a concentrated load P naught in the middle of this beam. So when we apply the equation of section, the method of section, we need to choose an arbitrary position x at which we are going to define the section, and we need to isolate the left or the right. So in this case, because there is a load in the middle, we will need to consider two cases, which is the case where x is between 0 and L, and then the case of x between L and 2L, because if we isolate the left and the right, the load that will be applied to the region that we isolate will depend on whether x is lower or larger than L. So we need to take those two cases. So we will need to first have the case where x is in between 0 and L, that is case 1. And then we will need another case, which is the case of where the section, the position x is going to be between L and 2L. That's going to be the second case. Okay, and in this case, we can decide to, after we have decided a given point x, we can either choose to isolate the left or the right. So when x is in between 0 and L, it's simpler to isolate the left. So we are going to isolate the left in this case. We could isolate the right and we would get the same result, but let's isolate the left. So if we isolate the left, then it means that now the portion of the beam that we isolate goes between 0 to the specific point x that we have chosen. Then we have NA, that's the external load at x equals 0. And then, so we have the internal load, P of x, at the point x. Again, internal load, we always define it to be positive as pointing towards the outside of the beam. Now, so if we do the same for the other side, so now we take a given x that is between L and 2L. In this case, it's going to be more convenient to isolate the right, even though we could also isolate the left and we will get the same results. So now if we isolate the right, so we will have the beam that starts at a specific point x that we choose. We isolate the right, so now the beam goes between x and 2L. We have the external load direction from the support NC. We don't know yet what it is, but for now we are going to express everything in terms of NC. And we have the internal load. And again, the internal load is always defined as pointing towards the outside. So now the internal load is going to be pointing towards the left. Okay, so now we are at step 5. We will move to step 6, where now we will write the condition of equilibrium for those isolated sections. So in this case, some of the forces along x equals 0. So what do we get? In this case, NA has a negative projection, and P of x has a positive projection because it's pointing towards the right. So what you find in this case is that P of x is equal to NA. So that's the value of the internal load. That's not the final result because we don't know what is NA, but at least at this point we find that the internal load between 0 and L is equal to NA. Same thing now if we isolate the right part for x between L and 2L. So now we have P of x that has a negative projection, and NC also has a negative projection. It's pointing towards the negative x. And then in this case, we find that Px, the internal load, is equal to minus NC. So again, this is not a final result because we don't know what is the value of NC yet. This is still an unknown, but this is an intermediate result. So now, so we have the method of section. We have isolated the region in both cases. So now we have calculated the internal load in terms of the unknown. Then the next step after this is step 7. Step 7 consists in now calculating the deformation. So here again, so we will use the elongation formula. The elongation formula, the general elongation formula, is that the elongation between A and B is the integral between A and B of the load divided by the cross section divided by the Young's modulus. So here, when we apply this formula, we always need to be very careful of those three quantities: load, cross section, Young's modulus. Do they depend on x or not? If they depend explicitly on x, then we need to solve this equation, this integral. If they do not depend on x, if they are constant over a given region, then we can take them out of the integral and we get a simplified formula, which is that the elongation between A and B is simply equal to the load divided by the area divided by the Young's modulus times the length between A and B. This is the simplified expression when it's only valid when the load, the area of the cross section, and the Young's modulus do not depend explicitly on x. So in this case, what do we have? The cross section does not depend on x. The cross section is constant. The Young's modulus also doesn't depend on x. It's made of a single material, so the Young's modulus is constant. However, the internal load does depend on x. It's equal to NA or minus nc, depending on whether x is it between 0 and L or between L and 2L. So in this case, we need to solve this integral. However, there is one thing that we can use, which is that the load, although it depends on x, the load is constant between 0 and L and between L and 2L. So here we can use one property of the integral, which is that if we calculate the integral of a function between a and c, we can say that this integral is the integral of this function between a and b plus this integral between b and c. So that's the additivity of the integral. We can always separate a given integral into two integrals by integrating over different portions. So in this case, it means that the elongation of the beam between a and c, the total elongation of the beam, we can always say that the total elongation of the beam is going to be first the elongation of the beam between a and b, so the elongation of this part, plus the elongation between b and c. So again, it means that the total elongation of the beam will be the sum of the elongation of each portion of the beam. Or another way of saying that is to say that the integral is an additive operation. So you can always separate the integration between a and c as the integration between a and b plus the integration between b and c. So in this case, it means that if we want to calculate the total elongation between a and c, which is what we have in the compatibility equation, we can calculate first the elongation between a and b, and then the elongation between b and c. And why is it interesting to do that? Because the internal load, although it depends on x, it is constant between a and b, it's equal to plus na, and then it's constant between b and c, it's equal to minus nc. So then, because it's constant by pieces, we can apply this simplified formula to calculate first the elongation between a and b, and then the elongation between b and c. So that's always something that you can use even if the load, for example, is not constant throughout the entire beam, but if it's constant by pieces between over different region, then you can apply this simplified equation. The only case where you would really need to solve explicitly the equation, the integral, is when you have either the load or the area of the cross section or the Young's modulus that is really a continuous function of x. So let's do this. So in this case, we are going to use this simplified formula here to calculate first the elongation between a and b. So we are going to apply this formula here. The only difficulty, the only thing to remember is that we need to replace each of those ingredients, each of those terms by their actual value. So if we want to calculate the elongation between a and b, so it is equal to the load. In this case, the internal load P is equal to Na. Then we need to input now the length between a and b. So the length between a and b is just L in this case. That's the distance between the point A and the point B. Then we need to divide this by the area of the cross section A. So in this case, A is constant over the entire beam. And we need to divide this by the Young's modulus, which is also constant. So this gives us, in this case, the elongation between A and B. We can do the same now to get the elongation between B and C. So again, this is equal to the load. In this case, the load is negative. It's minus NC times the distance now between B and C. The distance between B and C is also equal to L. But again, here this is just a special case. The distance between B and C is equal to L, but this doesn't have to be always the case. So you always need to be careful that you always replace this distance between the 2 points by its actual value for the prime that you are considering. Then you divide by the cross section, which in this case is the same throughout the beam, times the Young's modulus. Okay, so now we have calculated the two elongations. So now we can calculate the total elongation between A and C. It's going to be equal to the elongation between A and B plus the elongation between B and C. That is to say, it's going to be equal to Na minus Nc times L divided by Ae by combining the two equations that we previously found. Okay, so now that gives us now a new equation, right? Because if we use the condition of compatibility, now we get this new equation. We can replace delta AC by the value that we just found. So we would find that this term here, so Na minus Nc times L divided by Ae is equal to 0, which in this case, since L and Ae cannot be equal to 0, it means that simply Na minus Nc is equal to 0, or that Na is equal to Nc. So this gives us the second equation that we needed to solve this problem. So in this case, now we have two equations. We have the fact that Na plus Nc equal P naught, and now we have the second equation, which is that now we know that Na is also equal to Nc. So then what you can do is to combine those two expressions, those two equations, to find the value of Na and Nc. So in this case, what you would find is that since Na plus Nc equal P naught, and since Na is equal to Nc, then you can find the final result, which is that Na is equal to Nc and is equal to P naught over 2. So in this case, that gives you the value of the unknown. So in this case, again, that was the reverse approach, in the sense that rather than first calculating the load and then using this load to calculate the elongation, now we first calculated the elongation, and based on this, we were able to calculate the value of the unknown. So this is, in this case, a reverse approach. So now we have everything we need to solve this problem. So we found the value of the unknowns. And since we knew already what was the expression of the load in terms of the unload, then it means that now, so we can go to step 8. We can calculate first the internal load. So remember not to stop simply, if I'm asking you to calculate the internal load, don't simply write px equal plus Na when x equals 0 to L, or px equal minus Nc when x is in between L and 2L, because that's not a final expression. That's just an expression in terms of the unknown. So in this case, if I'm explicitly telling you to calculate the internal load, then I mean that you need to actually write px equal and replace this by the value of the unknown that you now have found. So in this case, what we need is the fact that for x between 0 and L, then p of x is equal to Na, and Na is p naught over 2. So this is the value of p of x. And for x between L to 2L, then the load is equal to minus Nc. So the internal load would be minus p naught over 2. So in this case, this is the value of the internal load. So if I'm asking you to draw the load diagram, then what you need is just to plot the value of the load as a function of x. So in this case, that would look like this. So you plot as a function of x for x going from 0 to 2L. You plot the evolution of the load. So in this case, the load is positive between 0 and L. It's equal to plus P naught over 2. And then the load becomes negative to P naught over 2 between L and 2L. So the load becomes like this. So in this case, the load is positive in this region, which means that in this region, the beam will be under tension, while in between L and 2L, the load is going to be negative, which means that the beam will be under compression. So now, based on this, you can also calculate the normal stress, which is going to be the end of this problem. In this case, this is what we wanted to begin with. So you can calculate the normal stress. The normal stress is always, the expression is always the load divided by the area of the cross-section. This expression always works. In this case, the area of the cross-section is constant. It's equal to A. The only thing that changes is the load. So the load is equal to plus P naught over 2 when x is in between 0 and L. So in this case, the stress is going to be equal to plus P naught divided by 2A. And when x becomes between L and 2L, then the stress will become negative. It's going to be equal to minus P naught over 2A. So in this case, this is the result that we want if our goal is to calculate the internal stress within the structure. And again, now if I'm asking you the stress diagram, then what we would need is to plot the value of the stress as a function of x. So we will need to plot the stress for every x ranging from 0 to L up to 2L. And so in this case, the stress in this case would show the same trend as the internal load with this step function like this, where the stress would go between plus P naught over 2A, so it would be initially positive, which again means that the beam is initially under tension between 0 and L, and then becomes under compression, where the stress becomes minus P naught over 2A between L and 2L. So again, when you're facing a statically indeterminate problem, you will always need to apply this method. What will change and what will depend on problem to problem is the specific condition of compatibility, the equation of compatibility, the specific geometrical condition that has to be true. This is going to change from problem to problem. But the rest of this approach, this general method, is always going to remain the same. Otherwise, you will always have to follow those different steps to solve statically indeterminate problems.